Welcome to lecture 8, in which we're going to talk about accelerated motion in 2D, which includes projectile motion. It's a very common type of motion, lots of examples in the book on this one, and we'll talk about what it is. Now, the principles we're going to need for this are essentially only things we've covered already. The idea of that each direction is independent of each other, like we saw in the case of the boats crossing the river. We are going to notice that algebraically speaking, the one thing that combines what happens in the x and y direction is the time, right? So when we solve a problem, we set up our equations, and the rest is just algebra, well then time will often be the one variable that kind of connects them both. As I said, we'll talk about projectile motion. In fact, the examples we're going to go through happen to be projectile motion examples. In the next couple of videos, we'll also be looking at circular motion and general turning motion, as well as motion where there's acceleration in both directions. And we'll do some example problems in this video too, and including, talking about the algebraic techniques. It's impossible to pretend there's math and there's physics, and we can do physics without doing the math, so this is very integral to getting good at physics. Let's start with an example, just to get to grips with it. So here's my example. I imagine there's a ball on the table, and we give it a kick. So there's some initial velocity. I'm going to call that initial velocity u. I could call it v, but it doesn't matter what I call things. So I'm going to call it u because maybe I want to use v later on for something else, some other velocity. Well, this table has a height h, and our goal is to figure out where will the ball hit the ground, right? So we can imagine what's going to happen. The ball is going to move. It's going to move all the way to over here, and we assume there's no friction, no air resistance. Nothing has been accelerating the ball while it's going up here. So when it reaches this point here, it'll still have that same velocity u. So the same velocity vector I've drawn in two spots, because the ball has that velocity here, and it still has it here. So what's going to happen next? It's going to leave the table here, and you can probably imagine what's going to happen. It's going to do something like this. It's going to end up here, then here, then here, and it's going to hit the ground somewhere over here. Right? It's the kind of shape you probably expect, just from having seen that kind of motion before. Now, we want to figure out what is the distance between the edge of the table here, so let's draw it like this, and where the ball hits the ground. So I'm tracking the ball. I guess I imagine I'm tracking the very bottom of the ball, because that's the part that's on the table, that's the part that hits the ground, but it doesn't actually matter too much as long as I stick with one in the same spot on the ball. I could have picked the middle to middle, right? Would have been the same height difference. So you want to figure out what this is. So we want this in terms of what? Well, in terms of u, the initial velocity. We can imagine if this is super fast, the ball is probably going to fly further. The height of the table, that's probably going to make a difference. And of course, what's making it fall in the first place? Why doesn't it keep going in a straight line? Gravity, somewhere along the way, we'd expect that gravity is going to feature as well. That's what we want to do. We imagine those other quantities are given, and in the end we're going to plug in some numbers just to see if our answer that we're going to get makes sense, but we'll leave that until the very end. Okay, so let's analyze this motion, right? So the motion up to here is boring. It's a constant velocity to the right. So this is where we really start looking at what's going on. Let's call this here our time equals 0 is here. Right? This is when we start our stopwatch. This is when the actual motion that we're analyzing starts. So the ball is moving in two directions, right? It's moving sideways and it's moving up and down. In this case, down. Now, let's give those directions names. So we're going to need a coordinate system. I'm going to pick my origin. Well, where should we pick it? We've got choices, right? I could pick it up here or maybe over here. I think I'm just going to go with the corner down here. I guess I just like that position. And one nice thing about picking it down here is that everything is kind of on the positive side. If I do it like this, if I make this and this, if I make those my two axes of my coordinate system, then everything happens within this sort of positive sector. That doesn't really matter, but it's kind of nice if fewer minus signs flying around. So I'm anticipating that. We call those x and y. Right? This is the convention. More often than not, we end up calling the horizontal direction x, the vertical one y. But you could call it whatever you like, and we will see example where we call it something else, or where we use x and y for some other directions. But right now, let's stick with this one. Because it'll make our life easier, and you'll see why. So let's ask what's happening in each direction. Well, in the x direction, right, in the sideways direction, there's nothing that's accelerating the ball. We assume there's no air resistance, or at least that air resistance is negligible. We write this here as the x direction. We have a constant velocity. We write it as a constant x velocity. Whereas in the y direction, the velocity is not constant. Initially, the velocity is 0, right? Here, this velocity vector is all in the horizontal direction, not up and down at all. But there's an acceleration in the y direction, and that is, of course, due to gravity. We've identified the two types of motions in the horizontal and the vertical direction. And every time we have a situation where one direction is constant velocity, one direction is constant acceleration, we'll call that projectile motion, because that's what projectiles do, right? This is a projectile that's flying through the air. When you hear that word, you might think of, I know, a catapult hurling rocks at a castle or something like that, or somebody shooting a cannon, some kind of projectile like that. But it's anything that flies through the air, for example, but it could also be other sources of acceleration. We'll come back to that to define it. We'll write it down in a little bit. Let's first deal with this problem that we're looking at right now. So, given that we know what type of motion it is, we can write down what the kinematical variables are. So, x, what do we have? Let's talk about the x direction first. In the x direction, I'm going to write this down here. So we have it. Then we can do the math afterwards. In the x direction, we have constant velocity. So, well, where do we start? It's called x0. We start at my initial x variable, right? It's right at the origin. The origin is here, so it's displaced in the vertical direction, but horizontally it's right where the origin is. Right? It's not left or right of the origin. So this is 0. Of course, this is going to be all in, I suppose, in meters, but right now we're working symbolically, so I'm going to leave out the units. And then the velocity, right? What's the x velocity? Well, it stays constant, so it is what it is at the beginning, and it's just u, because u in this case just points to the right. Right? It's not some funny angle where we'd have to take component. We look at that later. This one just points to the right. So that's it. So that means we can then write down what we know the initial position, we know the constant velocity. So that implies, those together imply that the x position as a function of time, right, is just u times t, because that's the velocity in the x direction. And so the way I've drawn it, I sort of anticipated that if I drew it correctly, this being a motion diagram where one ball picture is in equal time to the next one, then they should all be equal x distances apart. Right? So this distance is the same as this distance, the same as this distance, the same as this distance. Did quite well perfectly. I was eyeballing it, but that's what it should be. Okay. Now in the y direction, we have a constant acceleration. Right? That's what we said. The constant acceleration isn't just any old acceleration. It's of course, g, gravity, on Earth. So let's write down where we start. Though first, we start at some y position. Right? This is not at the origin. It is at some height, and the height is called h. So my initial y position, let me write like this, is equal to h, the height that's assumed given. Now, the velocity, I can't just write down what the velocity is because the velocity keeps changing, right? It's accelerated motion in the y direction. So, what I can write down is that the initial y velocity, right like this, is 0. Because initially, right, it has the velocity vectors to the right, it has no up or down component. But then it has an acceleration in the y direction, and that is of course g. And I have to be careful. I pointed my y-axis up, but g points down. So I'm going to make this negative, because it's the opposite direction. The acceleration is down. It's the opposite direction that my y-axis points. So that means I can write down what the y position is, right, as a function of time. It implies, because I know about accelerated motion, that everything we learned in 1D kinematics just applies here, except once in the x direction, once in the y direction. So here, that implies I get h, that's where I start, then v0t, well this is 0, so I'm going to skip that term because it's 0, and then a half at squared, so the a is minus g, so minus 1/2 g t squared. So now what I have is I have x and y as functions of time. Now, because this is accelerated motion, you can see the way I've drawn it, again anticipating it, the distance from here to here, like the vertical height lost here, is going to be less than during the second step, less than the third step, so it gets bigger and bigger and bigger downwards, which just gives us this shape. If I look at those, one little trick we can do is to actually figure out what is the shape. Like before we solve the actual problem, let's figure out what the shape is. Looking at those two together, it's kind of a little aside. Put a different color. The shape of this path. Well, let's have a look. Maybe you can guess. Maybe you read about it. But here's what I can do. X, right, is equal to ut. So one thing I can do right away, and we're going to need to do that, might do it later anyway, is that I write t as x over u, right? So I have, so use t equals x over u. So x is a function of time, right? I'm just rearranging this thing here. If I plug this in here, that implies that y as a function of x is going to be h minus 1/2. Now there's a t squared, so I'm going to plug this squared in there. G over u squared x squared. Y equals something minus x squared plus a constant. Well, minus x squared, whatever the constant that multiplies it is, that's a parabola. Right, so the shape that this type of motion describes, where one direction is constant velocity, one direction is constant acceleration, is going to be a parabola. Because here what is this saying? It's saying, look, you position your height above the ground as a function of how far to the right you are. The x position is given by an upside down parabola minus something times x squared, and then you add a constant, well, it just lifts the whole parabola up. If that doesn't make sense to you, review the math of basic parabolas, of how to draw functions and so on, because again, that's a skill you need to have. You've covered it for sure, probably in some pre-calc course, I suspect. So check your notes from that, or dig out an old book, or if you really have to, go online and find some quick tutorial video to remind you of those sort of plotting functions and parabolas in particular. Okay, let's go back to the actual question. So we figured out the x and the y direction. We're trying to figure out what is the distance traveled. So far, this was fairly straightforward. So what do I want to figure out? Well, what does it mean? Like, what am I asking? I want to find this distance. Well, what happens? What defines this distance? Well, it's defined by where the ball hits the ground, right? So we want the x position at the time of landing, let's call it that. That's what we mean by where does it hit the ground, right? Time of landing, that is, we want the x position at the time when the y position is 0, right? Because what determines this event is, okay, the ball has reached y equals 0. So we're translating the ball hits the ground into math. That is y equals 0. So let's use our equation that we have for y. So we have that y, let's call it the t time of landing, t land, is, so I know exactly what it means, that's equal to 0. Right? So let's plug in our expression that we have up here for y. So I can say h minus 1/2 g times t land squared equals 0. That is what determines the time of landing. So I can rearrange that to find the time of landing. It's fairly easy. I just, take this set aside. You know how to algebra. I want to get that it's going to be 2h over g, and then I'm going to take the square root. So make sure you can get from there to there. So in terms of height and gravity, this is how long it takes. In fact, we get this just from free fall as well. It's really, the y direction is free fall, right, which we talked about to a great extent. So this looks familiar because we've seen that kind of expression before. So now we say, okay, we've got the time of landing, the time the thing is in the air. Well, where is the ball at that point in the x direction? So now can find the x position of the ball at the time of landing. So how are we going to do that? Well, I've got an expression for x for any time, right? X, the time is this. So I'm just going to plug in here the time that I care about, which is the time of landing. And that was the thing is I defined as the distance d, right? So d is by definition x of at the time of landing. And that is just u times the time of landing. And that is, of course, just u times this, 2h divided by g. And that's going to be my final answer, right? So this is in terms of u, h, g, just as we wanted. Now we could sort of do a check. Does this answer make sense? One thing we can do is we can plug in a we can check the units, the dimensions. So this is going to be in meters. So let's do this dimensions check. And I should make something unambiguous here. So dimensions, we talk about dimensions, is it one-dimensional, two-dimensional, three-dimensional, but dimensions also means like what types of units. Is it a length? Is it an area? Is it a velocity? Like is it what type of units does it carry, right? So this is kind of a term that's used in more than one way. So maybe we should call it the units check instead. So D, it's often written in sort of square brackets, and you would just care about the units, is a length. So it might be in meters. Whereas the right-hand side, well, U is in meters per second. It's a velocity. I guess I'm being a bit inconsistent here. Written down the other way, doesn't matter. And then this 2h over g, the units of that, well, this is meters over meters per second squared. Let me write this down. So this is meters over meters per second squared, which of course is nothing but seconds squared, because meters cancel out meters, and 1 over second squared brings the second squared to the top, so it's seconds squared. We take the square root of that, we end up with seconds, right? So I've got u times the square root of 2h over g just checking the units now, is going to be meters per second multiplied by the square root of seconds squared. The square root of seconds squared is seconds, so that brings me to meters. Okay, that's the same as d. It's a length. Amazing. Okay, that makes sense. That doesn't guarantee that your answer is right, right? Because maybe the 2 should be a 4. Who knows, right? Maybe I got it wrong. Now I got this right. I guarantee you this. But you could imagine I made a mistake somewhere. Maybe I lost a 2, right? I still would get the same unit. So it does not guarantee that the answer is right. But if the answer was wrong, maybe I forgot to take the square root. Well, then this unit analysis would show me, hey, it doesn't work out. I would have ended up with like meter seconds. That's not right, right? So always check, or you can always check the units just to give you a sort of plausibility check. Can my answer possibly make sense? And the other thing we can do here, this was our answer, right, is that we can just plug in some values. A ball flying off a table is a fairly intuitive situation. Like, you kind of know what to expect, right? This is not some spaceship or atoms or who knows what, where you have no real sort of idea how big the number should be. So we are just going to do a plausibility check, which we can do in this case. So numerical plausibility. Again, it's not something you have to do every time, but it's something you can sometimes do just to check your work. So let's have a look. Our answer was D is equal to the launch speed, or the speed at the top, times the square root of 2h over g. So let's think of some realistic values. Let's say u is, let's go with 1.5 meters per second. H, how high is the table? Maybe 80 centimeters. So I'm going to go with 0.8 meters, right? 80 centimeters. And g, because we're on Earth. So I'm going to make this 10 meters per second squared, because 9.8 is kind of hard to deal with. Okay, let's plug this in. So then I get d is equal to 1.5 times 2 times 0.8 over 10. Take the square root. We do the math. That is 1.5 times the square root of 0.16. That happens to be 0.4. It's 1.5 times 0.4, which comes to 0.6 meters, 60 centimeters. That's a fairly realistic answer. Again, it doesn't guarantee that it's right, but I took 3 realistic values, out comes a realistic value, right? If I had plugged in those values and I'd gotten 200 million meters, you'd be like, wait a minute, something went wrong, right? But I got a plausible value. Okay, another sanity check that I can do for my answer. Alright, so this was the first example. Let's do another example where also something is accelerating under gravity. Here's our second example. Let's imagine you're a pirate, you're sailing the 7 seas. Turns out there are also other pirates, like those guys, here, this one here. Those guys here, and they took your treasure. So what you're going to do, you're going to roll out the big cannons, and you're going to fire at them. So we want to figure out, well, at what angle do I have to aim my cannon to hit the other ship? Now, of course, realistically, I have some kind of range, because the ship isn't a single point. Maybe imagine I want to fire at this point right here. Of course, I can't aim straight at it, because if I aimed like just horizontally, the cannonball would fly, but gravity pulls it down and would splash into the water. So I need to aim it up a little bit, and then I'm going to get a flight path that might look something like this. We know it's going to be a parabola again, because again, once the cannonball is in the air, the only thing accelerating is gravity, and it's always pulling down. So this is an example similar to the last one, and also an example of projectile motion. Now, we can't change the launch speed of the cannonball. So there's some initial launch speed, initial velocity vector here. We call this VL, L for launch. You could call it V0, or V who knows what. But but I'm going to call it VL because L stands for launch. So the ship, the target on the ship is a distance R, right, from where my cannon is to here. And I'm going to make the assumption that our ships are the same height, or at least the target is the same height as my cannon. And I'm going to assume this is on Earth. Yes, space pirates are fun, but these are not space pirates, these are normal sea pirates. Alright, so what angle should we aim our cannon at? Right, that is the question. So the way we're going to analyze this is, again, we're going to ask about motion sideways and motion up and down. Right? This is a sensible coordinate system to choose, where we have an axis that's horizontal, one that's vertical. Why? Well, because gravity acts straight down, so it only acts in one of the two directions. If you have a friend and they want to use a coordinate system that's sort of like this is the x, this is the y, let them do it, but it's not going to work very well. I mean, they're going to get to the answer, it's just a lot harder, or a little bit harder. So we're going to pick a sensible coordinate system. Now, maybe I'll pick my origin. Why not right here, just to keep my life simple? Origin can go wherever, but it shouldn't change the answer. But I'm going to make these my axes, x and y, just because I anticipate it'll make my life fairly straightforward. Okay, so let's look at the two motions again. Maybe take a moment to copy this down. I'm going to move the page up. We're going to look at x and y. So the x direction, again, there's nothing accelerating the ball, right? We assume the launch speed is the speed that the ball has, like the instant it's coming out of the barrel of the cannon. Right, so it's no longer being accelerated by the gunpowder, the explosion inside. No, it's now just in flight. Right, and it doesn't have any thrusters. There's nothing that keeps it going, or that applies a further acceleration. Right, it's just not being slowed down horizontally because there's nothing slowing it down either. So it keeps going at a constant velocity. So constant velocity, let me just write this here, parentheses, constant velocity. So we are going to have that, what is the x velocity? Well, is it VL? No, because VL goes in at an angle. So I need to find a component of the launch velocity that is horizontally, and maybe I just draw this a little bit bigger and squeeze it over here. Right, if this is VL, then there would be the horizontal and the vertical components. So this would be VL, its x component. This is going to be VL, the y component. Now we have to give the angle a name. Oh, it's called theta. So this is my angle theta, right? My launch angle. The angle above the horizontal. And so this is going to be VL, or it's the adjacent cosine theta. Of course, theta is the thing we ultimately are trying to find. It's constant velocity. So as a result, I can right away write down what my x position is as a function of time at all times. Namely, it's Vx times t, right, constant velocity motion, which I can write as VL cosine theta times t, because, well, VL is given, is assumed known, and theta is the thing we're trying to find. Okay, t is for any t right now, right? This expression, give me any t. Oh, 3 seconds? Okay, I can tell you what's the x position of the ball at the time 3 seconds. I haven't said this. We're going to assume t equals 0 is the launch. Just, again, keeps our life easy. Okay, so now the y direction. Well, the y direction is the vertical direction, right? So check. Don't assume y means vertical, right? There will be examples when that's not the case. Here it is. Very often it is. Here it is. So gravity acts down because it's on Earth. So constant acceleration. Maybe I'll start with that. So ay is going to be minus g. Again, it's minus because I'm pointing my y-axis upwards, right? But gravity acts down. Okay, so I have this part. Let me think. So I guess I can write down what the y velocity is. Vy as a function of time. Right? The acceleration doesn't have a time dependence. I mean, I could write a of tx minus g as a constant function. It's a bit, but it's really, for our purpose, it's just a constant, because we assume it's constant. So here we've got, what is this? So constant acceleration, and that means our velocity is just going to be the velocity we start with. And we're going to add to it the change in velocity, that's acceleration times time, by what acceleration means. It's minus gt. Right? Again, every step of the way, if something doesn't make sense to you, make sure you pause and maybe look back at your 1D kinematics, because this is where we learned this. So finally, I can just write down the y position itself. And that is going to be, well, it's accelerated motion. Okay, what height do we start at? We start at 0 height. If you let me write down in full first, y0 plus the initial velocity in the y direction times time plus 1/2 a yt squared, right? Accelerated motion. Let's plug in what we know. So initially we are at 0, right? This is, my origin is right here. This is where we start. We're at 0 height. 0. I'm not going to write this down because it's 0. Then here I have, excuse the smudge, the y component of my initial launch velocity, right, is what I drew here. So this is going to be VL, the launch speed, times sine theta, which is the opposite of the angle, so sine, times time, and then A is minus G, is minus 1/2 GT squared. Alright, so I have a position, the x position, an expression, and the y position, an expression. And everything is now in terms of things we know, we assume is given, namely VL here, and G, and then the time, right, these are both just functions of time, and finally the angle, and that's the thing we're trying to figure out. So now we need the condition in math, and we translate into math the condition, well, to hit that target. So how do I say in math the cannonball hits the target? Well, one way to say it would be, okay, look, I know the cannonball is going to get over here. So when the cannonball has an x position equal to r, then its y position must be, well, 0 again, because they're the same height. Right, so let's write this down. So, the cannonball hits the target. Well, how can I say that in math? In this particular case, because the target's the same height as the launch point, I can say when x equals r, the sideways position is equal to the distance that's given, right, the r, then the height of the ball is 0, right? If the height of the ball was not 0, it might be positive, then the ball would be up here. It might be negative, the ball might be down there. Then we've missed. So this is what we want. Okay, so let's call the time t, I know, impact, the impact time. So let's write this down. So in the x position, I can write like this. I'm going to write as r is equal to VL cosine theta times t impact, right? Because I have, that is, this is the x position for any time. Well, when the time is the impact time, and I don't know what that is, x better be equal to r, kind of by definition, right? The impact is when x reaches that distance. So and then in the y direction, well, how am I going to say this? Well, I have an expression for the y direction too. It's right here. So I have that 0, the y position, is equal to VL sine theta times t impact minus 1/2 g t squared. And again, that's impact. Let's see if I can squeeze it on the page. Barely. It clearly says impact. Okay. So, two things. I've got two equations, and there are two unknowns. I don't know the impact time. I don't know how long the cannonball is in the air, and I don't know the angle. In this case, what do I care about? I want to find the angle, so I want to eliminate the impact time between this. So now we go to doing algebra. We set up our equations. So we want, oops, sorry, I'm anticipating here. We want theta, so eliminate the impact time between those two equations. Right. So how might I do this? Well, there's more than one way, but I think the easiest thing would be to use the x one, and I'm gonna write t, so I'm gonna write just x, just so I know where this equation comes from. The x direction, t impact equals r divided by VL cosine theta. And I can take this, I can plug it into here, and and let's see what we get, I suppose, right? So plug into y. You're going to take this and you're going to plug it into y, the y equation. Right, by that I mean, of course, this one here. And what I get then is I get that 0 is equal to VL sine theta t impact. That's VL sine theta. Now t impact, I know what it is. It's this r divided by VL cosine theta. And then minus 1/2 gt squared. So minus 1/2 g, and then this whole thing squared. So it's going to be r squared divided by VL squared cosine squared theta. Okay. So we want to solve this. This is one equation now that contains just theta. We've eliminated the time, right? So that's one equation. The only unknown is theta, so we just need to do some more algebra to rearrange it. So manipulate this equation to find theta. That's going to be our method. When you solve a problem, it can be helpful to do the little sort of annotations that I'm doing. Just write down in a short phrase, what are we doing, right? If you just write a long list of equations, and first of all, it makes it harder for me to know what you're doing, or for anybody else who wants to look at your work, and maybe understand it, learn from it. Well, they don't know what you're doing, because it's just a bunch of algebra. If you have little annotations, then people can follow. Also, it makes it easier for you to find your mistakes. If you find your final answer is wrong, well, you can more easily check each step individually. Okay, so we want to manipulate this equation. Now, it's equal to 0, right? You've got sines and cosines. It makes it a bit tricky, and the cosine squared here. So let's simplify this a little bit. Here's what I'm going to do. I'm going to multiply everything by VL squared cosine squared theta, because I want to get rid of the fractions. So multiply, I guess, both sides. The left-hand side is 0, right? So it stays 0, by VL squared cosine squared theta. And that's not the only way, right? There are other ways, but that's what I think I want to do. So then I get 0, because 0 times this is still 0. That's equal to, so this has come up, but now there's a VL cosine theta gets cancelled out, but this is VL squared cosine theta squared. So I get a VL squared sine theta cosine theta times, actually let me modify this a little bit, just save me a step. I'm going to take this divided by r so that I can get rid of this r here, and then minus 1/2 g r, not squared because I divided by everything by r. Now make sure again you can follow to this line, so you're you're not lost, right? So make sure this makes sense to you how I got from there to there. Okay, so now I only have one sine, one cosine. That's still a bit strange to do. Well, let me just bring them to one side, I suppose. Sine theta cosine theta is going to be equal to gr divided by 2 VL squared. So make sure you can, again, you follow the algebra. Okay, so this is like, here you might be stuck. Because here, like, okay, sine, cosine. Okay, I can take the arc sine, but what if the cosine? Okay, what do I do here? How can I solve this? And so now comes I wouldn't call it a trick. Now comes a tool. Right? And the tool is, we're going to use what's called a trig identity. Trigonometric identities. Now you find them in your textbook. You can just go online and say list of trig identities, like Wikipedia has a fantastically long list. What those are is that they essentially are just a long list of relationships between sines and cosines and tans and whatnot else, cotan, everything, stuff you've never heard of. Some relationship, like a bunch of relationships between them just hold mathematically. Right? I don't ever expect you to remember those relationships. You might already remember some of them, like sine squared plus cosine squared is 1. Right? Any angle, sine squared of it plus cosine squared of it is 1. That's one you probably have met before. But it's a whole list of them, and they just all follow mathematically from the definitions of sine and cosine. Now, they can be super useful for algebra. And so what you have to be able to do is you don't have to remember them, because very few people do, there's so many of them, but you just have to remember that they exist. Because I can look at this, and I don't remember what the right trig identity is, but I know they exist, so I can check the list, check, my back of my book, or maybe check, somewhere online, and I can have a list of them, and I can find the one that's suitable for me. So it's part of your toolbox as, somebody who works with physics in one way or another. You might come across situations like this where they become useful. So what are we going to use here? Well, here we're going to use the one particular trig identity that says that twice sine theta cosine theta is equal to sine of 2 theta, so sine of twice the angle. Now, this looks strange. You wouldn't guess this. I wouldn't guess this. And you can prove it geometrically. You can also just check it right now. So you might pause the video, just plug in some angles, 30 degrees, 30 degrees, 2 times 30 degrees, right? Check that it works out the same. I'm going to guarantee you it will work out the same, right? No matter what angles you try. So in our case, that's a useful one. And, imagine I look through my list of different identities and oops, I found one that works. So, because I've got sine theta, cosine theta, so I can replace this combination with just 1/2 of this. I just divide by 2. So what do I get? I'm going to leave this so you can still see it. So we are going to get 1/2 sine of 2 theta is equal to gr divided by 2 twice lone speed squared. And now I can simplify this a little bit. So, this half is going to cancel with this. Then I get that 2 theta is the inverse sine, the arc sine of gr over, not the 2. We've cancelled out this 2 with this 2. Just VL squared. And I guess I want to go all the way. I can have theta equals 1/2 the arc sine of GR over VL squared. So those identities are just a algebraic technique to have at your fingertips when you deal with combinations of sines, cosine, tans, right? Where you can't just say arc sine. Well, you can't take the arc sine of this, because what do you do with the cosine? Arc sine of cosine, what is that? I have no idea. Maybe there's an identity for it. Alright. Now, the thing to note here is that when you take the arc sine, you often lose some information, right? Because there's more than one angle that gives you the sine of which is the same. So let's let me just draw this quickly. So care, there might be more than one answer, right? Because let's look at the sine function. So here's the, oops, you can't see this. Like this. Here we go. So if I plot theta, right, against sine theta, and I'm just going to plot it between 0 and pi, or 180 degrees. Let's go with pi. It's working radians. I guess it can work in both. Right. Here, well, imagine the value we get here is, I don't know, 0.5. Well, 0.5, this top point here is 1. Well, 0.5 might be here. And then, okay, there's more than one possible angle. There's this angle here, and there's this angle here, and they both correspond to a sine of 0.5. Now your calculator is going to spit out this one here. It's going to spit out the first one. But maybe this one's physically meaningful too. So we have to see, well, what range is going to be our answer in? Well, let's go back to the problem, right? We had pirate ships. Might have forgotten about it by now. Well, our angle is definitely going to be between 0 and 90. Right? It's not going to be less than 0. It's like negative, shooting downwards, probably not going to work. It'd never go back up. Probably not backwards either, not more than 90, like shooting this way won't hit that ship no matter what. So theta is going to be somewhere between 0 and 90 degrees. And just remember, we're doing physics, not just math. So for our ship, we have that 0 is smaller or equal to theta, smaller or equal to 90 degrees. Now, that means that the 2 theta, right, is going to be like 2, if I go back to this one here, 2 theta is going to be between 0 and 180. Right, if theta is between 0 and 90, then 2 theta is between 0 and 180. Now, what that means is that I do have to worry about the second point. So I'm going to get 2 answers. I'm going to take the sine, the arc sine, and I get 1 answer, and I also have to find the second one, just using the fact that this distance here is the same as this here. So from here to here is the same from here to here. Excuse me. Let's plug in some values to actually see this, right? Let's put some values to our ship in our cannon. So sample values. So let's have a start. So what we might say, okay, what's realistic here? Let's say the distance is 3,000 meters, so 3 kilometers. You know, you see the ship in the distance. The cannon is fairly good. My launch speed is going to be 200 meters per second. I think that's fairly realistic for sort of, you know, the type of cannon you put on that type of ship that we're imagining here. Okay, and of course we're on Earth, so G is 10 meters per second squared. I know 9.8, but let's be honest here, our life is easier if we stick with 10. So let's figure out then what our answer is. So the answer we had, right, was this one here. Actually, I'm just going to use this one here. So 2 theta is, I want to find theta, right? 2 theta is arc sine of GR divided by VL squared, which in our case is going to be the arc sine of 10 times 3000 divided by 200 squared. You can check that it's 30,000. That's going to be 40,000, 200 squared. So that's the arc sine of 3/4. Now what is this? Now at this point you probably get out your calculator or maybe your sine cosine table if you're old-fashioned. You do this, and so we're going to get that 2 theta is equal to 48.6 degrees. I want to check that. But that's this value here, right? 46.8. That's what our calculator spits out. And of course, for us, this is not 0.5, but 0.75, so probably more like somewhere over here. Okay, let me just draw this again. This is 180. Something like this. This is 1. 0.75 is here, right? And taking the arc sine means it's asking, okay, what angle gives us this value here? And we found that this is 48.6. But there's another one over here, and using the properties of the sine function, this here is going to be 180 minus 48.6 degrees, which is, I think, 131.4 degrees. That's my second answer, or 131.4 degrees. That's 2 theta, and so theta is going to be half of that, so 24.3 degrees, or what's this, 65.7. Okay, so those are my 2 answers. Interesting, right? So apparently 2 angles will work. That's what this is saying. Is that true? Yes, it is true. Let me just draw my little ships again. So here's my one ship, here's our ship. Here's the other pirate ship. I think they had a square flag. Right, and we are shooting our cannon from here. So we could shoot it like this. That's probably the 24. Or we could aim it a lot steeper, 65.7, that's sort of up here, and then probably do something like this. But it'll get there to the same spot. So 2 trajectories will both work. The only exception is if you have something you shoot at a 45-degree angle, well then it's gonna, there's only one solution. Because the other solution would also be 45. But that's not the case here. The case here is 24.3, so the other one here would be 65.7 degrees. Both will hit the target. That's what the math says. Now, what's the difference between them? Well, first of all, the target's going to get hit at different angles. In fact, you can fairly straightforwardly check that this would be again be 24.3 and this would again be 65.7. It's essentially symmetric. Also, it will take a different amount of time. I mean, the easiest way to see this is that this lower path has a higher x velocity, so it's going to get there faster. This has a lower x velocity, so it spends more time in the air and before it gets back to here. But both will be solution. If I were pirate captain, I'd probably go for this one here. Probably easier to aim, faster flight path, less time for them to drift out of the way. But mathematically speaking, there are 2 options. Maybe if I was not shooting a cannon at a ship, but maybe over a wall to hit the my sworn enemy's castle, and there's a wall in between, maybe I could get over the wall with this, right? So there would be application. So maybe if I try to throw a basketball into a hoop, I might be interested in this trajectory rather than this one, because this might hit the hoop, but from the side and bounce off. Get the idea. The math does not lie. Think about it carefully. Okay, this looked complicated, it looked long. We got there in the end. I want to emphasize something though, right? Even though this looked like a pretty complicated long problem, it took us 4 pages, actually it wasn't, right? Most of it was me rambling on about it. Really, everything happened here. We wrote down x, y direction, Then we translated into math essentially our objective, and then we did algebra, 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 and algebra is easy, right? You just have to be careful. Yes, there's this trig identity technique, and that's just something you need to be aware of, so you can sort of be like, oh, what do I do here? Trig identity. You don't have to remember them. But then it was just more, just a bit of more algebra. I guess I helped myself by drawing a graph, just to make sure I don't miss out on any possible answer. Arc sines, arc cosine, those are the dangerous little functions where you have more than one solution. And then I just did an example. Alright, so this was an example of projectile motion, this time very literally of a projectile. In general, projectile motion, we should perhaps write this down as the last thing. Just define it. One velocity, one direction, has constant velocity. The other has constant acceleration. And this is often due to gravity, but doesn't have to be. Although I think maybe our textbooks, certainly some textbooks, some authors define projectile motion specifically as being gravity, but I think that's defining it too narrowly. But we're just arguing over words here, right? But projectile motion refers to this situation where one direction has a constant velocity, one direction has a constant acceleration, and the technique is you write down in each direction, you put in the thing that defines the problem. In our case, do we hit the enemy ship? When does the ball hit the ground? You translate it into math. You do algebra, you solve it. Often you want to eliminate t, unless you want to know the time itself. Depends on the problem. But it's a very mechanical process to solve these problems. So once you've solved a couple, you should be in good shape. But with all of physics, you don't get around solving some problems yourself. Though I will go through a couple more with you in a follow-up video. Thanks for watching. It was a long one. Thanks for sticking with it. And good luck with your studies and practice.